All right, let's dive into a topic that sounds like it's straight out of an old alchemy text or a sci-fi movie. We're talking about the incredible natural process where one element can literally transform into a completely different one. Yeah, let's get right into it.
So, let's just start with that big, mind-bending question. Can one element really just, poof, change into another? I mean, for centuries, people dreamed of turning lead into gold. And the answer, believe it or not, is a huge yes. And the craziest part? It happens all on its own, in nature, all the time. And this amazing process is called radioactivity. Here's the deal. Deep inside an atom, you have the nucleus. If that nucleus is unstable, maybe it's too big or just has a weird mix of particles, it wants to get more stable. To do that, it spontaneously transforms. We call the original unstable nucleus the parent, and the new stable nucleus it becomes is the daughter. And this whole transformation follows a surprisingly simple universal recipe. It always looks like this. A parent nucleus becomes a daughter nucleus plus some kind of emitted particle. That's the blueprint for all radioactive decay. Simple, right?
Now, you might be thinking this sounds like total chaos, with atoms just falling apart randomly. But it's not like that at all. This process is governed by a super strict and, honestly, really elegant set of rules. We call them the conservation laws, and they are the golden rule of all this.
And this is the absolute key to understanding everything. The secret sauce, the golden rule, is this. You always have to conserve the mass number and the atomic number. So, what does that actually mean in plain English? Let's break it down. Before the decay, our parent atom has a mass number, which we call A, and an atomic number, Z. Well, after it decays, if you add up the mass numbers and atomic numbers of the new daughter atom and the particle that got kicked out, they have to perfectly equal the originals. Nothing is ever lost, it's just rearranged. It's all about balance.
So, we keep mentioning these emitted particles. What are they? Well, think of them as the agents of change. They're the little packages of matter and energy that get shot out during the decay, making the whole transformation happen. So, it's time to meet the particles. There are four main players in this game you absolutely have to know. First up is the alpha particle. It's basically just a helium nucleus. Then you've got two kinds of beta particles, beta minus, which is really just an electron, and beta plus, a positron. And finally, there's gamma, which isn't a particle at all, it's pure energy. Now look closely at their mass numbers and atomic numbers. Those are their fingerprints. That's how you tell them apart.
So why are we so obsessed with that atomic number Z? Because it's literally the element's ID card. It defines what an element is. If you change Z, you change the element, period. For instance, an atom with 83 protons is bismuth, but if it spits out an alpha particle and loses 2 protons, its Z drops to 81. And boom, just like that, it's not bismuth anymore. It is now thallium. It's a total identity change.
Okay, so we've met the crew, but what can they actually do? You can think of them as having different superpowers, and it all boils down to two things: their electrical charge and their ability to punch through matter. This makes it super clear. Your alpha and beta plus particles are the positive crew members. Beta minus, since it's an electron, has a negative charge. And gamma rays? They're totally neutral, no charge at all. And believe me, that difference in charge dramatically changes how they interact with the world. And check out their penetrating power. You might think the big, heavy alpha particle is the toughest, but nope, it's actually the weakest. A single piece of paper can stop it cold. Beta particles are a bit tougher. They can get through paper but are stopped by a thin sheet of aluminum. But gamma rays, they are on another level. They're pure energy, and they will blast right through paper and aluminum. To stop them, you need something really dense, like a thick slab of lead. So we know how these atoms decay, but what about when? I mean, how fast does it all happen? Well, it's not an instant thing. The timing is all figured out by this fantastic concept called the half-life.
The definition is really straightforward but so powerful. A half-life is simply the amount of time it takes for exactly half of a pile of radioactive stuff to decay into something else. The key thing to remember is that it's a measure of time, not amount.
Let me walk you through it. It's super easy. Let's say we start with a certain amount of a radioactive substance. We'll just call that initial amount M0. Now, we let the clock run for exactly one half-life. What's left? You got it, exactly half of what we started with. We now have M0 divided by 2. So what about after a second half-life goes by?
Well, half of the remaining material decays. So we take that half and we cut it in half again. That leaves us with just a quarter of what we originally had. It's this incredibly predictable, steady decay that makes the whole concept so useful for scientists.
And the range of these half-lives is just mind-blowing. I mean, look at this. For astatine-215, it's over in a 10,000th of a second. Blink and you miss it. For iodine-131, which we use in medicine, it's about 8 days. Then you've got carbon-14, the key to dating ancient fossils, with a half-life of 5,700 years. And then there's uranium-235 at 704 times million years. It's just staggering. So you see, this process of atomic transformation isn't just some abstract thing from a physics class. It's happening everywhere, all the time. It's the engine that lets us date history, power entire cities, and even treat diseases. It's a fundamental force of our universe. So, now that you know the blueprint, I'll leave you with this question to think about. Where else do you see the impact of this incredible force of nature?